Hello everyone and welcome to today's learning session. I am honored to present on behalf of Gudsky Research Foundation. Gudsky is dedicated to making AI and ML education free and accessible to all learners. Through our 6-month applied AI and machine learning course, we cover everything from the foundations of machine learning to advanced model evolution, deployment and real world applications. The idea is simple. Knowledge should not be locked behind barriers. Whether you are a student, a working professional, or a curious learner, you can join this journey and gain the skills needed for today's AI driven world. Our mission is not only to teach algorithms but also to ensure that learners understand why these methods work and how to apply them and how to evaluate them in real life projects. So, now we'll see why evaluation matters. So let's start with the big question, like why does evaluation matter in machine learning? When we build a model, it learns patterns from the data, right? But the real test is how well does it perform not only on the training data but also on new unseen data. Now, many people think accuracy is enough, but in regression problems, when we predict continuous numbers like house prices, rainfall, or electricity bills, accuracy is meaningless. Why? Because accuracy works for classification problems like yes or no, pass or fail, but not when the outputs are continuous. So, now imagine like this, we are predicting house prices, like here we mentioned like actual prices of the house is 50,000, 200,000, and another one is 1 million, and predictions are 60,000, 180,000, and 180,000. Now here, if someone just said this model is 70% accurate, that doesn't tell you the full story. Look closely, the house is worth 1 million, but the model predicted only 180k, a disaster in the real world. Here, as we see that in actual prices, they mentioned 1 million in actual price, but prediction goes wrong here. So it will be the major issue here. This is why we use evaluation matrices. Those are MAE, MSE, RMSE, R square. We'll see in further slides. Now we'll see basic, like what is MAE. MAE is average error in absolute terms. MSE means mean squared error, like squaring of the MAE penalizes large mistakes. RMSE means root mean squared error, error in the same units as the target. R square is coefficient of determination, how much variance in the data is explained by the model. So here in real world importance is, imagine a e-commerce company using a regression model to predict demand of our products. If the model severely underestimates the demand, they'll lose sales, right? If it overestimates, they'll waste inventory. Only proper evaluation metrics can tell whether the model is truly reliable or not. Without matrices, we can't deploy the models that look good but fail in real world case. Okay, now we'll move to the next slide, that is learning objectives. Before diving into details, let's outline what we learned today. Like first is understanding regression matrices, learning validation techniques, avoiding overfitting and underfitting. Now we will see one by one. Understanding regression matrices means we'll explore the meaning, formulas and intuition behind matrices like MAE, MSE, RMSE, R square and adjusted R square. You will see how each metric tells a different story about errors. Okay, now learning validation techniques. Learning validation techniques means how do we check if the model is generalizing properly or not. We'll go through train, test splits, k-fold cross validation, LOOCV and stratified sampling. Each method ensures we don't fool ourselves into thinking the model is better than it actually is. Okay, now we'll go for avoiding overfitting and underfitting. Overfitting means the model is too complex and memorizes most of the noise, and underfitting means model is too simple, misses important patterns. We'll explain the bias variance trade-off, the heart of building balanced models. So by the end of this lecture, you should confidently be able to say, I know how to evaluate regression models, select the right matrices and validate them in real world applications. So this is what the main objective of this session. Now model evaluation is in machine learning. Now let's define model evaluation in machine learning. Model evaluation in machine learning means it is a process of using matrices and validation techniques. We'll use both to judge how good a model is. There are two key pillars here. Okay, so remember it, like matrices and validation. Matrices means quantifying performance and validation means ensuring generalization. Okay, matrices here gives us numerical values to measure how closely predictions are to actual values. Example, if RMSE means root mean squared error is 2000 in a house price model, it means the predictions are on average of rupees 2000. Okay, and validation. Validation checks if the model can work on unseen data, means the data which is not trained the model still, and new data. As we say this new data, a model that only memorizes training data will fail in the real world, right? Here we'll take a real world analogy. Think of matrices as exam marks. They show how well you did on specific test. But validation is like solving new practice questions. It shows if you actually understand the concept, you will practice the problems and solve it. Okay, so a good machine learning model must have both strong matrices and solid validation results. That's what ensures reliability in deployment, whether it's predicting stock prices, sales or medical diagnosis. Okay, this is what model evaluation in machine learning. And what is regression evaluation? Regression evaluation is simply the process of checking like how a good regression model's predictions are compared to the actual values. Okay, why it matters? Like why is this critical? Without evaluation, you don't know if the model is useful or not. Evaluation tells us whether to trust or improve the model. Okay, and let us compare models here. Here if we take a real world example like electricity bill prediction, actual value is 2000 and predicted is 2050 rupees. So here error is 50. So it's good. Okay, and now we'll take one more example in same electricity bill prediction. Here actual value is 2000 and predicted is 4000. So the error is 2000. It's very bad, right? It's double the actual price. So it will not work. And if we take a real rainfall prediction as another example, actual value is 100 millimeters and predicted is 98 millimeters. So it's very close, like error is 2 and actual is another example. If we go, actual is 100 millimeters of rainfall and the predicted is 20 millimeters. It's terrible, it's not correct, like it's very poor prediction. So regression evaluation acts as quality control checkpoint before deploying, just like a car undergoes safety checks before hitting the road. ML models undergo evaluation before real world usage. This is what regression evaluation. And here there are types of regression problems. So as we talk about this, like there are two major types of regression problems. One is simple regression and another one is multiple regression. So we will see this one by one. Simple regression means uses only when one input variable to predict the outcome. Okay, it will take only one input variable to predict the outcome. So if we take an example of predicting a student height just from their age. Okay, and multiple regression means this will use two more input variables. Like if we take a house of an example, predicting house price using features like area, location, number of rooms, age of the building. So by considering all these things, we'll so this is known as multiple regression. Both types predict a continuous values like salary, weight, rainfall or prices. Okay, and also it's important to note that regression not equal to classification. Understand? Regression means it is used for continuous numbers like numerical values, and classification means used for categorying like separating two groups like categories like yes or no, pass or fail, spam or not spam. So distinction changes everything. The choice of matrices, the type of algorithms, and how we interpret results. So this is what the types of regression problem. And if we take an example, regression is like predicting how much a person will score in an exam. Like if we take an example of 85 marks, and classification is like predicting whether the person will pass or not. So this is what actually regression and classification means. Both are useful, but they answer very different business questions. So now we see true versus predicated values. In regression, we always deal with two kinds of values. One is true or actual values. I denoted here true value or actual value is y, and the predicated values as y bar. You can choose as your wish alphabet. So true or actual values means this is what really happened in the real world. Like what are the things we see in the real world. Example, a person's actual salary is 50,000, and the predicted values means this is what the model estimate like based on the given input features. If we take an example, the model predicts that the person's salary will be 48,000. So here the difference between them is called the error. So error equal to y minus y bar. So in this case 50,000 minus 48,000 equal to 2,000. So this is how we'll calculate the error. This is the foundation of evaluation. Every metric we use MAE, MSE, RMSE or R square is derived from these errors. In real world analogy, imagine a weather forecast, actual temperature equal to 32 degrees and predicted temperature equal to 30 degrees, and error is 2 degrees. If predictions are consistently close to the true values, the model is good. If they are not giving the actual values, the model is poor, so the predictions are wrong. So here the key takeaway is good models minimizes the gap between true and predicted values. Okay, this is what the true versus predicated values. And now we'll move to the next thing, error calculation. Like as we previously discussed about how we calculated the error, let's go a little bit deeper into error calculation. The formula is straightforward, like error equal to y minus y bar. But why are these errors are so important? Because they form the building blocks of all regression matrices. Example, actual temperature is 30 degrees Celsius and predicted is 28 degrees Celsius. So if we calculate the error here, 30 minus 28 equal to 2 degrees Celsius. And now if you have many data points, you calculate each errors, and then you combine them into single value like MAE or RMSE that summarizes the overall model performance. So let me take an example here. Think of a cricket batsman. Every shot he plays can be slightly off target. If you only look at one shot, you don't know how good he is. But if you calculate how far his average shots are from the boundary, you get a sense of overall consistency. Okay, hope you got it. And errors therefore are not just numbers, they are diagnostic tool to understand model reliability, like how actually the model is performing. Like it is giving the good examples like good predictions or poor values. So this is the very important in error calculation. Okay, and now we'll move. So we'll see mean absolute error. Mean absolute error means, in plain words, the average size of errors, ignoring whether there are positive or negative. Example, actual values are 10, 15, 20 and the predicted values here is 12, 14, 18. So error we get if we calculate 10 minus 12, 15 minus 14, 20 minus 18, we'll get the absolute errors like 2, 1, 2 and we'll add this and divided by 3. Why 3 means the numbers what we take that divided by 3. Like how many numbers we take, that many number divided by that number. Okay, that equal to 1.67. If we take a real world example here, predicting taxi fares, if MAE equal to 15, it means on average the model predictions are 15 away from the true fares. Okay, like less than or more than 15. Advantages of MAE is it's very easy to explain to non-technical people like who are uneducated or other uh, course related people like who are not into this field. Let's and also less sensitive to extreme errors compared to squared matrices. In practice, MAE is great when you need interpretability. Interpretability means like explaining prediction quality to business managers or clients. This is what mean absolute error. And okay, now we'll see the example of MAE. Let's walk through a slightly bigger example to really understand MAE. Here we take a data set like with actual house prices and predicated house prices. So we'll see the values like 100, 150 and 200 and predicated house prices 110k, 140k and 195k. We'll calculate the errors like by minusing the actual prices from predicated house prices. We'll get the absolute values like minus 10k and plus 10k and plus 5k. So with the absolute values we take the average, we'll get 8.33k. On average our model predictions are of about 8,330. It's if we if we see here an advantage, it's simple and intuitive and it's useful for business applications where stakeholders want an easy explanations. So this will be very helpful in business field. And here the limitations are a 5k error and 50k errors are considered as same, like equal value. It does not give extra penalty to large errors. That's why we use MSE or RMSE later. So if we get a small error, then that also treating equally, and also if we get a big error, same that also treating equally, which doesn't make sense, right? So with that we'll use MSE or RMSE for further exploration. And we'll see the mean squared error. Mean squared error means it's very popular matrices used to mirror the average squared difference between actual value means y and the predicated values means y bar. It shows like how far the predictions are real from or far from the real outcomes. Okay, here we given a formula like MSE equal to 1 by n summation of I equal to n, I equal to 1 and upper we'll see n yi minus yi bar whole square. Okay, yi means actual value, yi bar means predicated value and n equal to total number of observations. Here is the explanation of formula and we'll see the example here. Actual we'll see here 10, 15, 20 and predicated are 12, 14, 18. So from that we'll calculate errors. After calculated the errors, that means absolute values, through for that absolute values we'll square. So after squaring we'll divide with a number by 3, so we'll get 3.0. so this is the value of mean squared error. Okay, and The only difference from MAE is that we square the errors. Why do we do this means squaring ensures that negative and positive errors doesn't cancel each other out. Okay, most importantly, large errors are penalized more heavily here. Okay, this is what mean squared error. We see a quick example. Before that, take an example of mean squared error. Think of a teacher grading exams. Small mistakes like spelling errors are forgivable, but a huge mistake like leaving an entire question blank should cost more. Similarly, MSc ensures that large prediction mistakes hurt the score more and will get the less score. Okay, if you really leave a blank a question in exam, that means you will get less marks. It's okay if you leave some words, it's considerable and they'll give some marks. Okay, this is what MSc is useful when we care about avoiding big blunders rather than small slips. But keep in mind, since the errors are squared, the units are not the same as the target variable, which can make it harder to explain to stakeholders. This is what MSc. We'll see the example of MSc as we previously discussed about a small example. Now we see a big example. Actual prices and predicated house prices. That means model given values based on the given inputs. Here first step we will calculate the errors. Errors means absolute values. Okay. That means actual price minus predicated house prices. Then after that values we will square the values. Okay, which is called errors. We'll square the errors. By squaring the errors we'll get some value. By doing sum of squared errors we'll get value like 225. After getting the 225 value, we'll divide it by 3 because there we take 3 input values, right? We'll get 75. Here interpretation is MSc equal to 75. Shows average squared error in the house price prediction. Okay, and here the key points are large errors dominate the MSc and units are squared, making interpretation less intensive. But notice the unit is now squared 1000 of rupees, which is unintuitive. That's why in practice we often prefer root mean squared RMSE, which brings the error back to the same unit as the target variable. So okay, if you don't understand this, I'll give an example. Imagine presenting this to a real estate company. If you say MSc is 75, they may not understand what that means in real terms of real money. But if you use RMSE and say our predictions are off by about 9000 on average, they immediately get it. That's the practical power of RMSE. Okay, now we'll move to the RMSE. RMSE means it is a square root of MSc. It gives error values in the same unit as the target variable. Here we will see the formula. RMSc means root of MSc, root of 1 by n, summation of I equal to 1, and upper will have n, and yi minus yi bar whole square. This is the whole formula, and the definition is RMSE is simply root square. This small adjustment makes the metric much easier to interpret because it brings error back to the same unit as the target variable. So if we take an example here, if MSc equal to 9, then RMSc equal to root 9 equal to 3. Okay, this is what RMSc. In real world example, suppose you are predicting electricity bills. If RMSc equal to 500, that means on average the predictions are about 500 from the actual bill. This is what RMSc. Why RMSc is popular? Because it's widely used in industry and competitions like Kaggle, and it penalizes big mistakes like MSc, but also remains interpretable since it's in the same units as the target. So here we take a key point as if you ever want to explain model quality to a manager, client or non-technical stakeholder, RMSE is your best friend. It will explain the model very easily. Okay, if we take an example of RMSE, let's go through a dataset example for RMSE. Here we take an dataset example, actual rainfall in millimeters like 100, 150, 200 and predicted rainfall 110, 140 and 195. Errors are we get 10, 10, 5. Squared errors are 100, 100, 25. That means squaring the errors, and MSE means by average by sum of those three values and doing divided by 3 will get 75. RMSE means root 75 equal to approximate value of 8.66. So this is what the process of RMSE. Okay, on average our rainfall predictions are about 9 millimeters of. In real world connection, imagine a farmer deciding whether to irrigate his fields based on predicted rainfall. If the model is consistently 9 mm, that may be acceptable. But if the RMSE were 40 to 50 mm, the farmer could suffer crop damage due to wrong decisions. That's why RMSE is often preferred metric for applications where precision really matters. Okay. Now we will see R square. R square means coefficient of determination. R square means the proportion of variance in the dependent variable that is explained by the model. So that means now let's shift to gears from error based matrices to R square, also known as coefficient of determination. R square means the proportion of variance in the dependent variable that is explained by the model. Okay. In simple words, R square tells us how much of the variation in the outcome can be explained by our input features. Okay, let me take a formula here. R square equal to 1 minus SS RES by SS TOT. RES means squared residuals, means errors, and SS TOT means total variance in the data. And next, here the key points are R square ranges from 0 to 1. Higher R square equal to better explanatory power. R square equal to 0 means model is no better than just predicating the mean. R square less than 0 means model is worse than using the mean. So if we take an example here, R square equal to 0.90, it means the model explains 90% of the variation in the data sets. That excellent. Real world example, imagine predicating employee salary. If R square equal to 0.90, it means 90% of the salary differences can be explained by the features like experience, education and industry. Only 10% is left unexplained due to random factors like negotiation skill or marketing conditions. So this is what about R square coefficient of determination. If we take an example here, actual salaries are 50k, 60k, 70k and predicted are 52, 63 and 68. We'll get the values by minusing the errors and then by average we'll get 60k. With that 60k, the actual salaries and the predicted salaries can be minus, and then we'll do the square to both of them, we'll get some values. With that we'll do the R square, that is 1 minus 17 by 200 equal to 0.915 as shown in the formula. And here the interpretation is the model explains 91.5% of variance in salaries. Okay, this is what RES means. In the business, this is powerful. Suppose HR is using this model to forecast salaries for budgeting. With R square approximate of 0.92, they can be confident that the model captures almost all important patterns. Okay, now we'll see adjusted R square. Adjusted R square means Now we already know that R square tells us how much of the variation in the outcome is explained by the model. But R square has a serious problem. R square always increases when we add more predictions, even if those predictions are useless. This is misleading because a model with 50 features could show high R square, but maybe only 5 of those features are actually meaningful. That's where adjusted R square comes in. So here we see the adjusted R square formula 1 minus 1 by R square n minus 1 by n minus p minus 1, where n equal to number of observations and p equal to number of predictors. This adjustment penalizes models that use too many unrelevant variables. If we take an example here, a is to 2 predictors, R square equal to 0.90 and adjusted R square equal to 0.89, and model B 10 predicators, R square equal to 0.91, adjusted R square is 0.80. So we have to give the values to the formula, then we'll get some values. This is what adjusted R square. Model A is better even though model B has slightly higher R square. Okay. Here model B technically has a higher R square, but its adjusted R square drops sharply because many predictors don't add real value. So model A is better. Think of predicting house prices. You can add silly predictors like color of the front door or day of the week the house was listed. These might push R square higher slightly, but adjusted R square will punish the model for adding irrelevant variables. Always check adjusted R square when comparing models with different numbers of predicators. Now we'll take a matrix comparison here. Till now we discussed about all these MAE, MSE, RMSE and R square. MAE means mean absolute error. This is less sensitive to outliers. When to use means when all errors are equally important, and interpretation means lower MAE equal to better predictions. Okay. MSE means mean squared error, high sensitive to outliers. When we'll use this when large errors need to be penalized. Low MSE equal to better predictions penalizes large errors more. And RMSE means root mean square error, sensitive to outliers, where error unit need to match original data. That time we will use the RMSE. Row RMSE equal to better predictions and interpretable in same. In R square coefficient of determination, no sensitivity when measuring goodness of fit. We'll use when much outliers are there in matrices. We'll use the R square adjust, and then units as target variable between 0 to 1 equal to higher R square, that equal to better fit. This is what the matrix comparison. And residual analysis means, now let's talk about residual analysis. These are simply y minus y bar. In plain words, they are difference between actual values and predicated values. But here's the magic. Plotting residuals can tell us whether the model is reliable or not. So what do we want? Ideally, residuals should be randomly scattered around 0. Residuals here means 0. This means the model is unbiased and captures the true pattern. Okay. Warning signs are U-shape or curve pattern. That means model is missing some non-linear relationships. And funnel shape means variance is not constant. And large residuals means large error means possible outliers that need attention. Predicting exam scores, if residuals are systematically high for low performing students, it means the model is biased. Maybe it doesn't capture difficulties faced by weaker students. So okay, imagine you are throwing darts at the dartboard. If the darts are scattered randomly around the bullseye, that means good model. If the dots from a pattern like all clustering in the top right, something is wrong in your aim or in the model. So residual plots are like x-rays for regression problems. They reveal hidden problems. Okay. Now we'll see the overfitting versus underfitting. Now we come to one of the most important topics in machine learning, overfitting and underfitting. Overfitting means the model memorizes the training data including the noise, that means unnecessary data. Training error is very low but test error is high. When we train a model, it doesn't give any errors and the errors are less. But if we give the testing, it will get more errors. This is what overfitting. A student who memorizes last year exam answers but fails when asked new questions in the same syllabus. And underfitting means the model is simple to capture important patterns. Both training error and testing error is high. A student who barely study and performs poor in exams. So this is what the overfitting and underfitting. And okay, now here bias and variance trade-off means high bias means underfitting, high variance means overfitting. Okay, the sweet spot is in the middle where the model captures patterns without memorizing the noise. If we take an example of predicting house prices, underfit model uses only one feature like square footage. It misses location, age, etc. Predictions they'll give very poor. And overfit model uses 50 features including irrelevant like color of the house, when it was built. So those are doesn't needed for the model. So it will be correct in training data but it will fail in the test data. Okay, as a machine learning engineer, your job is to find the balance between bias and variance. Now we'll see the train test split. Now let's move into validation techniques, starting with the simplest, train test split. It is the one of the most common technique. The train test split is one of the simplest and most commonly used validation technique in machine learning. It involves in dataset into two parts majorly. Those are training and testing. Training dataset is used to train the model and help it in patterns and helps it to learn the patterns from the given data. And the test data is used to evaluate the model performance, and the unseen data means new data like how it actually working. And the process is randomly divide the data set into two groups. Train the model using the training data, test the trained model on the testing data, and compare the prediction like y bar with actual values using evaluation matrices as we previously discussed about like MAE, MSE, R square, adjusted R square. So these are the techniques we use to compare the predictions. And the common ratios are like how we split the data here is 70. Okay, here the data is in 100, like 100. We'll train the 70% of model and 30% of model is for testing, or else 80% for training, 20% for testing, and 90% for training, 10% for testing. So data set of 1000 records, here 800 for training and 200 for testing. This is what it means. Okay, in training and testing split is like studying before an exam. Training data equal to practice questions you studied. Test data equal to actual exam questions. If you only memorizes practice questions, that means overfit. If you fail on the exam, and if you only memorize the practice questions, you will definitely fail in the exam. If you didn't study enough, underfit, also you will fail. Train test plus split is quick and easy, but results can vary depending on how the data is split. That's why we often use more advanced methods like K fold cross validation. Now we will see k-fold cross validation. It is also an validation technique and a robust method. Like we'll see how it works. It is a dataset that is divided into k equal folds or parts. The model is trained on k minus 1 fold and tested on the remaining folds. The process repeated k times and the results are averaged. Here the formula is, if the dataset D is split into folds like F1, F2, F and so on Fk. So here 1 by k equal to summation of I equal to 1 and upper side will have k metric model train on D minus Fi, Fi. So actually how it works means, divide the dataset into k equal folds and train the model on k minus 1 folds. Like test it on the remaining fold. Repeat the process k times, each time with a different test fold. Take the average of all results and then we'll get the final evaluation score. Okay, let me take an example. Suppose we have 1000 records and choose k equal to 5. Each fold has 200 records. In round 1, train on F2 minus F5, test on F1. In round 2, train on F1, F1 and F3 minus F5, test on F2 until round 5. At the end, we average the errors across all 5 rounds. For real world example, think of a teacher grading a student by giving 5 mini tests instead of one big test. The final grade is the average of all 5. This gives the much fairer measure of performance. And here the advantages of k-fold cross validation: more reliable than the single train test split, as we previously discussed about that. Reduce bias caused by lucky unlucky splits. Uses all data efficiency for both training and testing. Okay, that's why in competitions, research and professional projects, k-fold cross validation is the gold standard for model evaluation. Okay, now we'll see the 5-fold cross. So here we take the 5-fold cross validation. Let's expand the idea of k-fold cross validation with a concrete example using 5 folds. Here we take this as step-by-step process. First we'll take the data set, like shuffle the data set, split into 5 folds like F1, F2, F3, F4 and F5. Train and test cycle should be like this. Like for round 1, we'll train F2 plus F3 plus F4 plus F5 and we'll test the F1 fold, and round 2 train F1, F3, F4, F5 and test the F2 and continue this process until round 5 and get the average, and after average we'll get the final score. If we suppose after 5 rounds we get RMSE values as 4.5, 4.8, 5.0, 4.6 and 4.7. Average RMSE equal to, by adding all those numbers and dividing them with 5. There we'll get 4.72. Instead of relying on one split, we now have much more reliable measure of the model performance. In real world analogy, think of hiring an employee. Instead of judging them based on one interview, you run them through 5 different interviews. By averaging across all 5, you reduce bias and get a fairer assessment of their true ability. So this is what 5-fold cross validation. And we'll see the leave one out cross validation, that is L over CV. And next, which is okay, this is an extreme version of k-fold CV. So definition of leave one out cross validation is k equal to n, where n equal to total number of data points. Here we take the data points, that means every iteration you train on n minus 1 samples and test on one left out sample. This repeats n time, so every single data point get used as test case exactly once. So if we take an example, we have a data set of 100 records. In first iteration, train on 99, test on 1. On second iteration, train on 99 and test on next one. Repeat this 100 times. At the end, you will get the result of all 100 test runs. Advantages is makes maximum use of available data. So in the data set, every single data can be touched and done by the process, and particularly useful when the data set is very small. So in real world, imagine a class 30 of students. To see how each student performs individually, the teachers gives an one-on-one oral exam to each of them. This ensures everyone is tested fairly, through it's time consuming. Okay, and LOOCV is computationally expensive for large datasets, but with small datasets it works well. So this is what leave one out cross validation. Now we'll see the stratified sampling. It is a technique which is especially important when working with imbalanced datasets. So the problem is, if you split data randomly, you might end up with train and test sets that have different distributions of the target variable. This leads to biased evaluation. So the solution is stratified sampling. Stratification ensures that a distribution of the target value is preserved in both training and testing sets. Example, suppose you have a medical dataset of 1000 patients, 8% are healthy, 20% are sick. If you do a random 80-20 split, you might end up with 85% healthy and 15 sick in training. That biases the model. With stratified split, both training and testing set maintain exactly 80% healthy and 20% sick. So in advantages, if we see, preserves the target distribution, like it will give the fair evaluation, like it will evaluate the result accurately and reduce the bias, which means errors. In fraud detection, if we take an example, in fraud detection only 2% of transactions are frauds. If your training set accidentally have 0.5% fraud cases instead of 2%, your model will definitely fail. Stratified sampling ensures the fraud ratio is consistent in both train and test data. Okay, now we will see the validation curves. Validation curves are powerful visualization tool for tuning models. So definition of this is, a validation curve plots model performance, train and validation against a specific parameter. So here we take the axis, x-axis and y-axis. X-axis here is hyperparameter and y-axis is performance matrices. And hyperparameters are polynomial regularization, and performance matrices, as we previously discussed about the MAE, RMSE, all these. So how to interpret these means, high train score plus low validation score, that means overfitting. Low training plus low validation, underfitting. Balanced train and validation score is optimal model. So if we take an example of polynomial regression with 1 to 10 degrees, degree 1 straight line, both train and validation error are high, that means underfitting. Degree 3 train and validation error are both low, that means optimal. In degree 10, train error is very low but validation error increases, that means overfitting. Okay, if we take example of cooking pasta, undercooked too simple for model, this is underfitting. Overcooked means too complex model, overfitting. Perfectly cooked pasta means optimal balance. Validation curves help to see where our pasta is perfectly cooked, the right model complexity. Okay, and we'll see the learning curves. Learning curves means, finally for this blog, let's cover learning curves. A learning curve shows model performance, like training and testing as a function of training data set size. It shows whether like adding more data will improve more performance of the model. Okay, x-axis here will take training set size and y-axis performance matrices. So how it interprets means underfitting means training and testing errors are both high and adding more data doesn't help. Overfitting means training is very low, training error, but test error is high. The model memorizes instead of generalizing. Good fit here is train and test errors coverage close to each other at low error level. Okay, this is what good fit. An example, if we train a model with 100, 200, 500 and 1000 samples, as the data set grows here, test RMSE decreases steadily and eventually stabilizes. This tells us model benefits from data, but beyond a certain point, adding more data won't help. So think of learning a sport like tennis. If you only practice for 1 hour, poor performance underfitting. If you only practice against the same partner and memorizes their moves, you play well with them but lose to new opponents like overfitting. If you practice consistently with different partners, you develop general skills like good fit. Learning curves shows whether collecting more data will improve your model or not, which is very valuable in real world projects. And now we'll see the overfitting. Overfitting means one of the most common mistakes in machine learning. Overfitting, as we previously discussed, when model learns more irrelevant noises in the training data instead of useful data. So the symptoms are the model performs well on training data but fails badly on new test data. Okay, if we take an example of r square equal to 0.99 and test r square is 0.55, the model looks almost perfect in training, but in reality it can't give the correct results. And for the causes of overfitting is model is too complex. That means it learns more from the other things, and insufficient training data, and the training data is lack of information and lack of regularization. That means penalty terms, and consequences here are predictions are unreliable. That means unexpected. Model can't handle new data. In business this means bad decisions. Okay, imagine a student preparing for exams. Instead of learning the concepts, they memorize past question papers word for word. In actual exam, if new question paper appear, they fail. That's called overfitting. So how we detect overfitting means, now we'll see the signs of overfitting. That means we'll have the low training error but high testing error. Validation curves, it have training scopes goes up, validation score goes down. Example, train RMSE equal to 2.0 and test RMSE equal to 10.0. Train R square equal to 0.95, test R square equal to 0.40. The gap between training and testing performance is a red flag. So here we have the more differences between these values. So how we detect the overfitting means by training testing split and cross validation and learning curves. As we previously discussed about all these, overfitting is like an actor rehearsing only one script. In rehearsal they shine, but when asked to improve in a real play they freeze. The gap between practice and reality reveals the problem here. So this is how we detect the overfitting. If we go for underfitting, model is too simple. On the flop side, let's look on the underfitting. It is too simple to capture the underlying patterns in the data. Symptoms are both training and testing data, it will have more errors. Suppose if you try to fit a straight line, that means linear regression to data that clearly follows a curve. Here we see that train RMS equal to 15 and the test RMS equal to 16, the model fails everywhere. Okay, here the model fails to capture the complexity more, and the causes of this is oversimplified model, too few features, that means less features in the dataset, not enough training data, and ignoring important relationships in the data. So if we take an example of student who only skimmed the textbook once, they don't memorize this, but they also didn't understand concepts deeply. As a result, they perform poorly both in practice and in exams. So underfitting equal to model has high bias, it can't learn from the data. Now we will see the detecting overfitting. So this is actually bias variance trade-off, which means the bias variance trade-off describes the balance between two source errors. Okay, and here error decomposition is, as we see the formula, error of x equal to bias x square plus variance of x plus sigma square. Bias square means error due to wrong assumptions, that means too simple model, and the variance means error due to model sensitivity to fluctuations. Okay, and noise means random variation in the data that no model can eliminate. The trade-off means the simple models high bias low variance, that means underfit. Complex models low bias high variance, that means overfit. The sweet spot is in between. So this is what the bias variance trade-off. If you take an example, think of archery, high bias, all arrows land far away from the bullseye but clustered together. High variance means arrows scatter all over the board. Balanced means arrows cluster around the bullseye. Key takeaway is good ML practice is about finding the right complexity that balances bias and variance. If we see the regularization technique here, regularization means the solution to the overfitting. Regularization adds a penalty to large or extreme model weights. This discourages the model from becoming too complex. Common types L1 regression and L2 regression and elastic net. L1 regression means lasso, penalty equal to summation of Wi, and this encourages sparsity. Some weights become exactly 0, that means the error will become 0, useful for feature selection. And the L2 is regularization, that means L2 regularization means ridge, penalty equal to summation of Wi square, shrinks weights smoothly, useful when all features matter but should be controlled. So here in L2 regularization ridge, we can't make the values exact 0, but it can be controlled. Elastic net means combination of L1 and L2 balances sparsity with smoothness. This is what elastic net. If we take an example, predicting house prices with 20 features, without regularization, the model might give huge weights to irrelevant features like color of the mailbox. With L2 ridge, the weights are shrunk, making predictions smoother. Okay. With L1, you remove unnecessary items completely. Regularization makes models simpler, more stable, and better at generalization. For cross validation for model selection means, now that we know all about cross validation, let's see about model selection. The problem is, suppose you build 3 models like linear regression, polynomial and random forest. Which one should you choose? Just looking at training accuracy isn't enough, because one might be overfitting. So here we take the process of k-fold cross validation. Train each candidate model on k-1 fold, test on the remaining fold, repeat for all folds, averages the performance, compare the model based on their average score. If we take an example, linear regression RMSE equal to 5.0, and polynomial regression RMSE equal to 4.2, and random forest RMSE equal to 4.0. Random forest is the best choice because it consistently gives the lowest RMSE across folds. Think of this as a cooking competition. 3 chefs prepared the same dish, and instead of one judge deciding, you have 5 judges. Cross validation folds. Each chef's score is averaged across all judges, and the best chef wins fairly. Cross validation ensures that the selected model generalizes well and reduces the risk of picking a lucky model. Okay, this is what the cross validation for model selection. If we take the house prediction example, now let's put everything into a practice with case study. We want to predict house prices based on features like location, size, number of rooms, age of building, right? Here we'll take the steps. First, we preprocess the data like handling missing values, encoding the categorical features like location, all these things, and splits the data like testing, training testing, or k-fold CV as your wish, and training the multiple models like linear regression, polynomial, random forest, and finally we'll evaluate the models like using MAE, MSE, RMSE, and R square. Example results are linear regression RMSE equal to 50,000, R square equal to 0.72. In polynomial regression, RMSE equal to 45,000, R square equal to 0.80. Random forest, the value is 38,000, R square equal to 0.88. Here the random forest is the winner. So in all of these we have the less error is random forest. This kind of model could be used by real estate companies like banks or online property platforms. Okay, like how this will show like how evaluation matrices guide us to choose the most reliable and model for real world deployment. Okay, now we'll compare the models like if we see linear regression, first it predicts the target value using target variable using a straight line relationship with features like y equal to b0 plus b1 into x. Example predicting house price based on size. So here we'll take only one value, that means house price or based on size. Okay, 1200 square feet. Prediction equal to y equal to 50 plus 0.3 into 1200, that means 410. Okay, here we'll get only one value, and in polynomial regression we'll get the more than 2, that means non-linear relationship. Here the formula is mentioned there. Predict growth rate over time with curved trend the model. Okay, here the formula is R square equal to 1 minus SSRES and SS total. Okay, and now we'll see the evaluation matrices. As we previously discussed about this, R square means coefficient of determination, and RMSE is root mean squared error, and MAE means mean absolute error. As we previously discussed about all this topic, and visualizing the errors. Here we'll see the errors like residuals means errors here. The errors which are touching the line, those are the errors which are near to 0. And also here in distribution of errors, we'll see in this bar, in this diagram we'll see that errors are near -2 to 2. So here the value of errors are more. And the key takeaway on matrices is MAE is simple and less sensitive to outliers, and RMSE penalizes large errors sensitive to outliers. R square means variance explained by the model. Okay, Here MAE having the more errors and RMSE having the less errors. That means MAE will actually simple and it will don't have the capacity of reducing that much errors, and RMSE having that much capacity, and variance explained by the model. That means R square, it can easily identify the errors. And also here train test split, quick single split may not be the representative. Okay, this is what about the matrices. And key takeaways on validation. Validation means, as we previously discussed about training and testing split. So there we see the in diagram, training is one part and testing is one part. Those are divided into two sets, and then after training we'll get the results. And cross validation means, like, if we take those three as, so those three boxes as training and those two for testing, so using multiple validation sets, this will give the correct values than the train split. Okay, so the best practices are always evaluate with multiple matrices. Like, if we use only single metric, then the model will fail. So we have to combine like MAE, RMSE, R square. So then we'll get the model performance better. If we take an example, MAE gives average error, RMSE penalizes large errors, and R square shows variance. So by combining all these, we can get the good result. And cross validation is, it is a robust estimate. Okay, like, we'll estimate the model performance and reduces the risk of overfitting to a single train test split. If we use k-fold CV, it averages the performance. Like, it here we see that training and testing robust model selection, and also we take the k-fold CV. So if we take the fold 1, fold 2, fold 3 as training, fold 4 for testing. So in this way of cross evaluation, make the good model choice. So regression evaluation and regression matrices are completed. Now we'll see the purpose of measure prediction accuracy and ensure generalization. So here all about the summary. Now we'll see that true versus predicated value, as we discussed in the first slide. That means true means real value and predicted means the error value. So predicted value, and finally we'll get the error value. Regression types means there are multiple types of regressions, and matrices there we used MAE, RMSE, root MSE, R square, adjusted R square. And validation we use the training, testing split, k-fold CV, LOI CV, and stratified sampling. And also we discussed about overfitting and underfitting, like how to reduce the overfitting, like, and how to detect the underfitting, and bias variance trade-off, regularization by penalizing the terms. So best practices are use multiple matrices, apply cross validation, visualize the errors, and learn the curves data efficiently. This will help out to get the better model. Imagine deploying a demand forecasting model for an e-commerce platform. If you ignore error plots, you might miss seasonal effects like holiday spikes. This could lead to inventory shortages or oversupply. So, best practices make the difference between an academic model and a production ready model. Okay, this is, and with that we conclude today's session on evaluating regression models. Let's reflect on what we covered, why evaluation matters, different regression matrices like MAE, MSE, RMSE, R square, adjusted R square, and validation test techniques like train, test, split, K-fold CV and L/over CV, and how to detect and fix overfitting and underfitting regularization methods, and finally a case study with all these parts and concepts. This lecture was part of Gudsky Foundation 6-month applied and AIML free education series. Thank you so much for joining today. If you found this valuable, don't forget to share it with your friends and stay tuned for the next lecture in this series.